Hello, let's take a look at another situation that can occur and related to lines and circles. And here we're going to look at two secant lines to a circle that intersect at a point X. And there's sort of three cases to look at. Case one, the point X, the intersection point is on the circle. Case two, it's on the exterior of the circle. Case three, it's in the interior of the circle. Actually, we're going to look at that backwards. We're going to look at interior first and exterior for case three. Okay. Case one, if the two secant lines intersect at on a point on the circle, then there's an inscribed angle there. And we've already studied that. We've shown that it intercepts one arc, and that arc has a measure equal to twice the angle of the inscribed angle. Or in other words, the inscribed angle has a measure 1/2 the measure of the arc that it intercepts. That is a very important result that we end up using lots and lots. We talked about that already. And we can think of this first case as sort of being the limiting case of the other two cases, as one of the arcs degenerates to a single point. Okay, so let's look at case two, where we have a pair of secant lines intersecting at a point inside the circle, in the interior of the circle. And so we're going to start by looking at this application right here, this GeoGebra app that Mr. Brzezinski put together here for us. And now he doesn't have the whole secant lines. He's just got the important part for us, which is the two chords to the circle. That's just got all the relevant stuff here. Okay, we can control this by these control points. This controls the size and location of the blue arc. This controls the end of one of the arcs there, and we can control the intersection points. This is the point I'm calling X right there. Okay, so we could phrase this in terms of secant lines intersecting at a single point in the interior of the circle, or we could just talk about two chords intersecting. So let's see if we can take this and do some work with this. Now we're really interested in this angle right here, this one that's kind of shaded in from here to whatever this point is over here. Okay, that angle. And notice it has a vertical angle over here. So this angle is going to intercept the pink arc, and its vertical angle is going to intercept the blue arc. We're interested in the measure of that angle versus the measure of these two things here. See if you can watch the animation here and see what happens as we slide this up. Now, if we go to here, these are radial segments, and then the measure of this blue arc is going to be the measure of this central angle, and the measure of the pink arc is the measure of the central angle here. So if you look right here, the pink now is half of the measure of the pink arc, and the blue angle is half the measure of the blue arc because we've done angle bisectors. Now what happens is we're going to rotate that around and bring it down here, and then bring the other one down and rotate it, and look what happens. It perfectly matches this angle that we were looking for. So can you see the result that we're looking for? If you add these blue and pink, you get it down here. The blue and the pink are each half of the original arcs. So I think from that you can probably get the result that we need. Okay, so here is my app for the same thing here. I think I've got it right here if I can get to it. All right, we'll just get to it this way. Okay, there it is. There's the point X, so you can make it be on the circle in the interior or the exterior. So I got all three cases here. If it's on the circle, let's just go back to case one first, and then you know that this arc only this angle intercepts this one arc of the circle, and of course it's got a vertical angle here that doesn't intercept anything. And that inscribed angle is going to have a measure 1/2 the measure of this arc. So we know about that already. So let's look at this case two, where these are intersecting in the interior. Okay, R will change the radius of the circle. X, A, and B are your control points. Okay. So suppose we have something like that. How does that How does that compare? So there's the measure of that. Let's look, and we can see the measures of the angles. So here, the measure of arc DC or CD is the measure of angle COD, which is given by this purple marker here, 0.37 radians at the moment. And this angle AOB is the measure of this arc, which is 0.76 radians. Remember, we're talking about arc measure, not arc length, which is something a little different. Okay, so anyway, how does the red angle compare to these two is basically what we're asking. Okay, and if you notice in this case, it's somewhere between them. Okay, does it stay that in between? Yeah, so we can maybe look at those measures down here. Angle X is 0.43 radians. Angle arc AB, which is a central angle, measure 0.57 radians. Arc CD is here. It's this 0.29 radians. Okay, I've got to fix that. Sorry. Okay, now we got it fixed. So angle arc CD is the 0.29 radians. Here I've added those two together, AB and CD, 0.87. I've subtracted them. In this case, that's a negative number because this one is bigger down here. But if we subtracted the other way, it would be 0.28. And remember something about these angles being half. So what if we double this angle X? If you notice, that matches the sum. So it looks like the measure of that angle is 1/2 the sum of the measures of the two arcs. It's something we also saw in the other app, right? So here we can move these things around, get some different measures, but this one and this one are matching. Okay. To make the picture work well, you need to have these things in the order A, B, C, D going around the circle, around positive direction counterclockwise. Okay, if you notice every time those two match up. So that looks like we have that. Now, can we prove it? Okay, well, that's where these extra line segments here, these chords, BC and AD come into place. Now, if you look at some things here, what do we have? Well, we've got this angle here, DBC, intercepts this arc, and so it's half the measure of that one. And this angle C here, that's the angle ACB, intercepts the blue arc, so it's half of its measure. But the red angle is the angle at X there, we've got marked, that is AXB, is an exterior angle to triangle XBC. So the red angle is just adding the measure of the red angle there, angle X, is just adding the measures of angles B and angle C together. But each of these is half of the original, just factor out a half, and you find that we just measure these two angles here, add them up, and then divide by 2 to get the red angle. And there's the proof. Okay? So here is the, there's the write-up of that, okay? To write it up formally, so you can read that if you want. Pause the screen if you'd like. Okay, now what if you get two angles that intersect in the exterior of the circle? Okay, once again, we've got an app that Mr. Brzezinski put together. Let's take a look at that. Okay, so here we have secant lines that intersect out here. We don't really care about the part of the lines that keeps going on out here and out here and out here. We mainly just need these really secant line segments going out this way, these chords, and extend them out till they intersect out here. The red points, the big points here, control things. That one we can move around. The white one controls the size of it. There's the center, so forth. We can control that there. Okay, so let's slide this slider and see what we see here. Notice that this is going to intercept two arcs of the circle again, just like it did when that point was on the inside and we had the secant lines. And we want to see what this has to do with the measure of this angle up here at the where the vertexes and where they meet, and how that compares to the measure of these arcs. So let's see what we got here. Okay, so look what we've got here. We've got a couple of inscribed angles here, which these points could be put anywhere, like say here and here. They could be anywhere, okay, because it'd be the same size angle. Look at the size of that angle and that one. Okay, look what's going on here. So those are the sizes of those two angles. How does it compare up here? Bring that blue one down here. Take it away from the pink one, and what's left over is the light colored one, which is what matches. So you guys catching what's happening here? Okay, let's look at it numerically again. Okay, so let's bring this point X outside the circle here. So now we have, again, we have two angles that it intercepts. It intercepts this arc AB, intercepts this arc CD. Okay, so that's our setup right there. Now, if we look at some additional angles here and some measures, how do they compare? So let's make sure this thing is measuring correctly. 1.04 is the measure of this red one, the X. Measure of arc AB here should be the same as this measure here, 0.56, that's right. CD should be this one out here. Okay, that one's not right. Let's fix that. Okay, now these are fixed. So let's see where we are at the moment. This angle, red angle, angle X is 1 radian at the moment. We've got arc AB is 0.45 radians. That's the blue one right here. That arc, that angle. 2.45 radians is that central angle, which is the measure of that arc, the purple one, from C to D. If you add those together, you get, you see, 2.9. If you subtract them, you get 2. And if you double X, you get 2. Oh, look at that. Those match up, those last two. Let's see what happens if we change it around. Yep, the last two are still matching up. Can experiment with that. Pull this out. Let me get in here close. Go further out here. You want to do it in such a way to get things to work out. These points A, B, C, D need to go around the circle in a positive manner like that. We can make the circle smaller or larger and it still works. Okay, so that seems to check out. Looking at the line segments and the angles, let's see if we can prove this one. Well, let's see. We notice we have, okay, look at this purple angle right here, this angle at B. That's the angle DBC or CBD. That angle is going to be half the measure of this purple arc because it's an inscribed angle. Look at this angle up here at D. That is the angle XDB or ADB, same thing. That angle is inscribed in the circle with intercepting the arc AB, so it's going to be half the measure of the blue arc. So this one right here is, this blue one is half the measure of the blue arc, or half the measure of that angle there, central angle. This purple one is half the measure of the central angle, in other words, half the measure of this arc. But the purple angle, that is DBC, is an exterior angle to triangle A or XBD. XBD. So the exterior angle theorem for triangles, Euclidean geometry, says the measure of this purple angle here, this exterior angle, is equal to the sum of the measures of its remote interior angles. Put that one there and that one together. Well, that one, so then, well, how do we find x then? Well, x is going to be the measure of the purple angle at B minus the blue angle there at D is going to be x, but each one of these is half of an arc, or yeah, half of these intercepted arcs. Factor out the 1/2, and we get that this angle x is 1/2 the difference in the measures of the two arcs. When it's inside, it's half the sum of the two arcs that are intercepted, and when it's outside, it's 1/2 the difference of the two arcs. So these two match up on the exterior, and these two match up. This one and this one match up on the interior. Okay, so that's an interesting setup there. Okay. Okay, there's the pictures, there's the statement of the proof, statement of the theorem, there's the proof. Okay, and in the next video we're going to come back and look at these same constructions, but instead of looking at the sizes of the angles and the arcs, we're going to look at the sizes of some of the line segments that are formed.